On this channel, we speak a lot about hardware and the research that goes into it and how we make silicon devices, and especially recently, how that pertains to machine learning and AI. One of the key metrics, however, in all of this isn't performance. It isn't teraflops, it isn't ops, it isn't power, it isn't memory bandwidth. It's simply the economics of running it all. I mean, I'm pretty sure a lot of you at this point have played with something like a ChatGPT or a large language model or stable diffusion or image generation. The problem is, at the end of the day, money is there to be made. The only reason that a lot of these things exist is that everybody in the chain has some sort of value add that they can get. And the issue is, right now, the economics simply aren't there. Today's video is all about how the economics of large language models has to apply to everyone in that chain, especially you. If you like this content, there are multiple ways to support the channel. You can like and subscribe this video, and many thanks for doing so. There's also Patreon, which gives you access to our Discord. There's a merchandise store and a newsletter, links in the description. For all of you who do contribute, thank you. You are keeping me well fed. Now, in this video, we cover the semiconductor industry, and we mainly talk about the economics of making chips. This here is a demonstration wafer of laser light sources. However, it's more than just making chip, where somebody has to make the money. On top of the chip builders, there are also the system designers, there are the operators, there are the software, and then ultimately the people who use that software as a service. The economics have to be that everyone in that chain needs to make some money to be viable. Now, the latest in our industry to drive a lot of those economics is the introduction of machine learning. The rush for machine learning enablement has put money into every layer of that stack in order to build a business case at the end of it that ultimately long term makes everyone in that chain some money. Right now, the economics are kind of screwed. There is a lot of VC funding propping up this market, whether you're talking about chip design, whether you're talking about data center, whether you're talking about application layer, lots of investment going into the hardware and software to build the ecosystem around AI. Now, of course, there are a couple of exceptions to that rule. As I'm recording this, NVIDIA has just had their financial report, and again, yes, they're making money. Turns out people who make the tools can make a lot of money out of it. However, as we go up that supply chain, aside from companies like Supermicro in that stack, very few are actually generating revenue from it. And the question here is, what do the economics of machine learning look like such that it becomes a sustainable, viable business? If you have the opportunity to speak to investors, they'll start talking to you about how there has to be a proper business use case in order to optimize for machine learning. And particularly here, we're talking about large language models. The way large language models have come into this space means that you need a lot of memory, you need a lot of compute, you need a lot of memory bandwidth. You need to be able to support that. You need to support high density cooling apparatus if you want the latest and greatest. You then have to make sure your software stack on top of that is rigid, and then you have to position it as a service or at a price that makes sense. Or perhaps you're a business that needs their own hardware, their own internal models to help your own users do so. That's kind of the IBM model: use hardware, use software, and then use it for a consultancy business, rather than just selling AI as a service direct. What's important here is one of the limitations in that scaling is just simply the cost effectiveness of enabling large language models. The reason why I bring this up is I'm here at Hot Chips. I've been in the Bay Area for 2 weeks, and I've noticed a very distinct change in the conversations I'm having around machine learning. For the last 2 years, pretty much since GPT came on the scene, everybody's been speaking about how user interacting with a model and the model giving the user a response. This is a simple user to model, user to agent type of workflow. The key metrics in that are, how large is or how accurate is the model. Typically, you need a lot of memory capacity for that. Then you've got the time to first token, which is when you get the first output. Also you have an ingress of tokens and an egress of tokens, but usually time to first token output is usually measured. That's a compute-bound regime typically. And then you have tokens per second. This metric we're hearing from a lot of AI hardware startups about being able to supply 200 tokens per second, 1,000 tokens per second. And that's more of a memory-bound regime. And I think it's important to realize here that the way that machine learning as a workload moves forward will showcase how exactly the hardware side, and then by consequence the software side, drive some of those economics. So if we're talking about user to model, that's going to be very user output focused. And then once you hit about, say, 100 tokens per second, maybe even about 200, you start thinking about how do we increase throughput, total throughput for our hardware infrastructure. That's where you get a funky graph like this one, where there's a trade-off between batching requests and tokens per second as like an instantaneous output, and then the total throughput per second from the whole system. This gets worse and worse as we talk about bigger and bigger models, because we have to deal with multiple GPUs or ASICs, because we're essentially limited on memory capacity. When we move into the sort of agents to agents, so this is where models talk to each other. Sometimes it's called agentic. You're dealing with, say, a user puts in a request, and the request goes into a model, and based on the output, the model may go to another model, or this model, or that model, and you may end up with like a daisy chain of multiple models. Now, that daisy chain essentially has input token, output token, input token, output token, input token, output token. So if you have a daisy chain of 3 models, the number of tokens you need in total has probably gone up by 3x, and that 3x is your cost, and your latency for that chain has also increased because you're now doing input, output, input, output, input, output. And you've also got to have the overall latency of that chain suitable for the user who submitted that one request. If you are already right at the limit of your time to first token with one model, you can't daisy chain to 3. So when we hear about hardware talking 1,200 tokens per second, that means that you can support 6 200 token per second models end to end, assuming you're not in a compute limited regime, because that tends to be memory bandwidth limited. These are the discussions I'm having right now with a number of companies in this industry, and especially as model size is getting bigger. We're going from Llama 3 7 billion to 40 billion to 400 billion, meaning you need 7 gigabytes of memory or 40 gigabytes of memory or 400 gigabytes of memory. It becomes a hardware problem. And right now, the hardware from most companies tends to be pretty much compute focused. We're dealing with one GPU with a lot of compute. It's got some HBM memory, up to 144 or 288 gigabytes of HBM on the latest and upcoming models. That feeds in at terabytes per second, and then that maybe talks to, say, 8 A6 or 8 GPUs, in a fabric, and then that goes out onto the Ethernet. One of the things that's happening, and I'm really surprised that this trip I'm speaking about it a lot, is that one of the companies that I work with, IR Labs, is having a presentation in a couple of weeks at the AI Hardware Summit. This video is probably going to go out around then. At the AI Hardware Summit, about how the economics of the future of machine learning, the future of this sort of agent-agent methodology, doesn't work out with the current fabric paradigm. Now, just to be clear, the IR is an optical I/O company. They're developing lasers and I/O chiplets to enable things to talk to each other faster. Right now, if you go look at the latest standards of Ethernet, we're talking about 800 gigabytes a second. If you talk about the latest fabric technologies from Infinity Fabric or NVLink or UA Link, then they're in the sort of 900 gigabytes per second regime. The point of optical is that not only do you get a higher bandwidth than those, you also enable a greater density of bandwidth, and also ultimately a lower latency of bandwidth by exchanging what is a copper link with a optical I/O link. I'm going to put up this graph because this is a graph I come up with after speaking to the people here. What you have at the bottom is, your HBM layer effectively. You've got one ASIC, or what is, from the software perspective, one ASIC speaking to 6 HBMs or 8 HBMs. On top, that's kind of like your, scale in solution. Then you've got up to 8 GPUs or ASICs in this sort of all-to-all configuration. It depends on which company you're getting, but most of them right now deal in that 8 way. You can arguably go up to 64 with some unique designs, and then NVIDIA is also talking about 72 using NVLink with their latest Blackwell system that's coming out next year. But ultimately, that's the limit of where direct ASIC to ASIC connectivity stops, and we're calling that scale up, how you can put the fabric into the system. Then after that, you have to rely on slower Ethernet, which again is approaching 400 gig or 800 gigabit Ethernet, in order to go beyond that small fabric. And ultimately, that's where some of the bottleneck lies. I've spoken to a number of people deploying large AI machines where they're having to simply buy other boxes of 8 ASICs in order to just increase their memory capacity to even fit those models. So it becomes a different equation of economics altogether. What needs to change in the middle of this, and this is part of the reason why there's an economics discussion on all of this, and what needs to change in the hierarchy so that people actually get a cost-benefit analysis further down the road, is that we need to scale out from 8 chips or from 16 chips to 256 chips to 512 to 1024. The thing is, if you want to go beyond a rack with copper electrical interconnects, that's kind of a limitation here. The distance to enable copper and electrical connectivity is half a rack at best, 1.5 meters. Maybe if you're smart, you can go across 2 racks, or you have to daisy chain multiple racks together. The benefit of optical, just in general, is that you're more limited by the speed of light than you are anything else. So we're talking about a foot per nanosecond in terms of latency, and with an electrical connection, you're already dealing with microseconds of latency. The goal here is that if you have the ability to daisy chain, just chain in an all-to-all configuration more than 8 chips together, so we get this 256, 512, 1024, which are going to be needed as we go down the sort of agentic large model route, which is what we're all predicting for the future. You need to enable that layer of fabric connectivity before you get to Ethernet. Now, don't get me wrong, Ultra Ethernet Consortium, that sort of thing, they're going from 800 gig to 1.6 terabytes and everything else, and they're scaling up and out. The vision here is that not only do you have the 8-way fabric, but you also have that 8-way fabric connected via fabric to more ASICs down the line, whether that's groups of 8 by 8 and then you have 8 groups of 8 and then they're all connected in an all by all, or it's literally a purely all to all 256 connections. I'll put up some diagrams showing what I mean. It becomes a complex problem to solve, and part of the complexity there is just simply developing the hardware to do it. Like I said, I'm here at IR Labs. They've graciously let me use one of their meeting rooms to film this video, because they're one of the companies at the leading edge of this. Now, I should say, the terminology used by some of these companies does change a little bit, whether you're speaking about optical I/O, which is what IR Labs tends to use. Broadcom, for example, uses co-packaged optics, and then you've also got integrated silicon photonics. The whole point here is that you take one of the chips, and what I showed the wafer here, this is like their early first-gen prototype on display. You put that as a chiplet connected into your ASIC, and you can put 4, you can put 8. Some of the demo slides I was being shown here and stuff that's going to be shown at the AI Hardware Summit by IR is 10 chiplets, and the point is you can configure those to talk to as many as you need, as many other ASICs as you need. One other differentiation here that I think is important is that it's not just about ASIC to ASIC. It's not just about that compute. With optical, you can also essentially extend to more memory. So imagine having, and again, the demo example that the guys have shown me here, is you have your standard ASIC with 8 HBMs, but 10 I/O chiplets. And those I/O optical chiplets could go to a bank of a terabyte of memory. So yes, you are adding in like another tier of memory, but now that ASIC has access to fast HBM and also high bandwidth optical connectivity to a terabyte of GDDR or DDR or something else. That ultimately is where a lot of this goes. I've been saying for a while, and it's due to some of what I'm seeing out there. Compute right now, machine learning compute can either be compute bound or memory bound, and so many of these companies are focusing mostly on compute and on a memory bandwidth. There's a few out there that are differentiated on that, but it means that when you look at their tops per watt, for example, because they've dedicated, say, half their power budget to connectivity, in order to make it so it's a more balanced regime between compute and memory bandwidth, and you plug it into a standard economic model, it becomes difficult. And that's why some progression has to be done in terms of how you put this fabric together. Now, yes, it could be solved by simply adding more memory and more bandwidth. However, the growth of performance of a memory like HBM 3, 3E, 4, 4E, Samsung was giving us details of that on their forum a couple of months ago. The roadmap is there, but machine learning is moving too fast. It has to get to this point where right now in 2024, when we get to say 2026, we need to be able to support 256 512 of these ASICs together, and not just relying on some proprietary technology. The discussions are being made, and because there is there's going to be a presentation from the IR guys at AI Hardware Summit as this goes live. I sat down with the CEO Mark Wade to talk to him about what he feels is, how do we solve this problem in the industry? Because it's not as simple. They are a connectivity company, so they are going to be talking about connectivity, of course. But I think Mark's, the models that they've developed here, I don't often see companies in this space talking about the economics, the end-to-end economics of a solution, regardless of technology. Usually companies like this, especially with engineering-focused CEOs like Mark, often talk about technology, leading edge customer, and then the scope for the revenue is simply within that ecosystem, and the endpoint cost, overall TCO, is more like an afterthought. Whereas some of the models I've seen, and hopefully I'll get to show some of them on camera, goes into some of these metrics and posits hypotheticals of where do we need to be in 2 years with GPT-5, 6, 7, GPT-8. How many models, how many parameters for inference are we going to need in order to enable an agentic workflow for some of these solutions? Even though often when we speak about machine learning at the highest level, we're talking about dollars per token, which is essentially a function of revenue per throughput. And we were speaking earlier about how you're meeting with investors, and it's like, well, in today's world, who really is making the money? It's the people making the pickaxes, right? The people making the tools.
Yeah, that's right. In the market world, investors have realized that as we head towards an AI-powered world, we have to go through a phase of transforming and solving all the underlying hardware inefficiencies that are built from having a set of hardware that was geared at a previous generation of applications and products in the market. So that's a good thing for everyone working on hardware, because it's driving a lot of interest down into the nuts and bolts on how things are actually made. And we have to keep reminding ourselves that the goal is to drive to a cost structure that end application builders have enough headroom in the value stack and how the dollars and pennies are flowing to have an end business model that can make money. So a lot of what we're focused on is the dramatic throughput per dollar per watt improvements you can get whenever you go re-architect your systems to really look at solving the system level set of performance challenges and cost challenges on running AI workloads. And in that analysis, to build big, high-performing systems, They're strongly limited by connectivity today. So that's where the kind of nuts and bolts of connectivity start to come in.
So when I look at the market, and when I look at say the models that exist today, even Llama 3, 70 billion, 405 billion, people talking about mixture of experts, 1.8 trillion. I kind of feel like that memory bandwidth and memory capacity are essentially everything right now, right? People, again, like I say, buying more memory controllers, essentially trying to buy capacity. We've got features like CXL coming down the road that could help solve some of that. We're seeing HBM3, HBM4. But I think based on conversations we've had today, because I've spent kind of all day with these guys so far, is that it's too slow.
Yeah.
It needs to get better.
That's right. And maybe to kind of back up and look at the big picture, 4 or 5 years ago, when the transformer models came out and we started entering into this new regime of AI models in transformer-based architectures, the model size also exploded. So number of parameters, and we passed this point back in, let's say 2018, 2019, to where you could no longer fit these single models on a single piece of, or a single chip, single GPU, single accelerator. So the model size and the computation that was required got spread across multiple connected GPUs and accelerators. And that's when the kind of first element of this connectivity limited regime was coming in. But the reason it got spread out is whenever you go spread the computation onto multiple pieces, it effectively multiplies the memory bandwidth that you have access to.
I think one point to focus on in all of this is where exactly the future systems are going to be housed. I spoke a little bit about it with Mark, but when you're dealing with all the data centers that exist in the world today, most of them are power constrained and physical space constrained. You're not going to get anything out of those that infrastructure if you simply put 2 big GPU boxes and that consumes all the power and uses all the cooling capacity, or you've had to install liquid cooling in able to support it. I've been speaking with companies at Hot Chips this week when I'm filming this, who are specifically designing their ASICs to work in air-cooled environments because they know the infrastructure of machine learning data centers, especially ones that are already built, can't handle with the future power per rack demands that some of these high-end ASICs need. The way I've been describing it is that a standard data center colo is running about 8, 10, 12 kilowatts per rack. You'll see some with like dedicated AI racks that will do around 25, 30 kilowatts. Then you have AI data centers that are specifically built, dedicated to run high-powered chips. They can do 40 to 50 kilowatts per rack. At Supercomputing 2023, I saw the first 85 kilowatt rack design. I've got a small short about that, and it's funny because it was a prototype that looked kind of beat up as they transferred it. And now NVIDIA is talking about 120 kilowatt racks, massive, as Mark said, heavy racks with all these cables, with all this compute, with a fabric that extends to the NVL72 type of workload. The point is, we have to go and enable beyond that with existing infrastructure. That means air-cooled, that means 12 kilowatts per rack, that means a limited amount of rack space. And the way to do that is by enabling chips that are efficient and that can scale and can bring that fabric together, so we're not just simply limited by 8-way ASIC designs as we have been for quite a while. Another benefit that I think Mark touched upon is simply that you can reconfigure these networks, especially in the cloud when we're talking about lumpy workloads. I didn't go into this much earlier, but the way we look at workloads today, training a big model is a very fixed workload. You know how long it's going to take, what accuracy you're going to get out of it, what GPUs you need to run it, and it's a very fixed, boxy workload. Fine-tuning is like a similar sort of thing, but usually done on a smaller scale. But it's a fixed workload with a fixed cost. That's why you hear numbers like it cost OpenAI, 10 million to train this model, or 15 million to train that model, or it cost Google 60 million to train this model. The problem as we go forward is actually inference, because inference, when you're using the trained model, is a lumpy workload. There'll be some times of the day you'll get more inference requests than others. It's like in the UK, we call it the effect of putting on the kettle to make a cup of tea, to boil water for a kettle during the middle of a football match because of the halftime break. That puts a massive strain on the resources, and so we get this need for leveling out power capacity on the grid. When it comes to inference, when it comes to the data center, the workload is going to be lumpy because at certain times of the day people make more requests than others, or the need for a deeper agentic pipeline is needed more than others. That means that the economics of AI have to scale, but it also means that if you can reconfigure your network on the fly during low capacity times, you can almost increase your throughput intensity or increase your time to first token through an agentic workflow. And then as the demand scales up, you can reconfigure the network to enable pipelining of those models, to give the best economics at that time of day to enable it. One of the things that most investors are pretty fixed on is that the future of revenue in this business at the top end, selling capacity on cloud to customers, is actually going to be the driving factor. I think most people think about cost spend in the AI space right now is to do with training. And that's because we hear these big numbers from OpenAI, from Google, from Meta, from others, when in reality the billions and billions of dollars that companies that deploy these systems are going to make is going to be on the inference side. So it's important to get that end-to-end strategy where we can talk about having 512 GPUs all interacting together and not just 8 to make those economics work. I mean, there is a ton of slides in Mark's deck. I've tried to help them prune it down to make it more effective for a 20-minute talk at the summit, but they're not wrong. They're not wrong. Everybody, in order for this business to work, and I know some of you are pretty downbeat on this business, but I know a lot of you are upbeat on what it can bring to the table. The economics have to work end to end. If there's a part that fails, that's going to be problematic. And one of the benefits of having multiple chips work together with an optical I/O fabric is that it can help make those economics work, especially where we're going to be in a few years with the size of those models and the way that machine learning is changing. It appears to be a more agentic workload. So if you're interested in learning out more, I'll put a couple of links in the video description, but I have to bring this wafer back on screen again because it's my minimum specification. I get hungry. And in case anyone was wondering how you get the optical into these chips, well, it turns out you have the lasers. This is the new 16 wavelength supernova laser here at IR Labs. And it's designed to be a pluggable module, and it goes pew, pew, pew with the light.